In our first calculus course, in which we were learning about derivatives, we learned that there are these things called second derivatives, and that's essentially just taking the derivative of the derivative. Now, that told us something about the concavity of the function. For example, if I were to think about a parabolic function that maybe looked like this, I would expect the second derivative to be less than 0 because this is concave down. And remember, concave down like a frown, easy way to remember that that is the shape of concave down, concave up like a cup. And this would have a second derivative greater than 0. And the reason is because it tells us the change in the rate of change. So here, notice the rate of change is negative, and then slightly less negative, and slightly less negative, and now positive. So the change in the change in the rate of change is positive, right? The slopes are increasing, and that's exactly what the second derivative tells us. In this case, the derivatives are getting slightly smaller and smaller and smaller, and they become negative, which is still smaller and smaller and smaller. So these slopes are actually decreasing, and that's what the change in the rate of change tells us. Now, when we get into the context of multivariable functions, it gets a little more interesting and a little bit more complex because we have not one input axis, x, but we have two input axes, x and y. So we actually have 4 different second partial derivatives. There's the 2 that are going to be familiar. These are just the regular second derivatives. So if you take the derivative with respect to x first, and then with respect to x second, you get the second partial derivative with respect to x. And if you take the derivative with respect to y, and then take the derivative of that with respect to y, you get the standard second derivative with respect to y. Now, these are called pure second partial derivatives, just because they are exclusively with respect to one variable, but you can also take the derivative of function with respect to the other variable after taking the derivative with respect to the first variable. So that's where we get f sub xy. And f sub xy means you take the derivative with respect to x first, and then with respect to y second, and here with respect to y first, and then with respect to x second. Now, that is the nice shorthand notation. If you wrote this in derivative form, of course, it just looks kind of nasty, but the second derivative, this is not d squared f dx squared. We like to read it like that, but that's not what it is. It has nothing to do with squares. It is actually the derivative with respect to x of the derivative of f with respect to x. That's how we would really write that for it to make sense. And then for whatever reason, because we have these two d's, that's why we write the superscript of 2, and because here we have, dx and dx, we write it as dx squared. That's the only reason for it. Similarly, like, for example, here, notice that the first derivative was with respect to x, and then the derivative of that with respect to y, versus here we have the derivative of f with respect to y, and then the derivative of that with respect to x. And these last two here are the same as the 2 here. So these are what we call mixed partial derivatives, and these are the 2 pure ones. I prefer these notations for obvious reasons. A lot less notation than having to write the derivative operator. Okay, so let's just practice taking the second derivatives here. So here is a multivariable function. So we first need to start by finding the 2 individual partial derivatives. So f sub x, remember the way we handle this is we treat x as the variable and we treat y as the constant. So 2y squared x, y is a constant, so 2y squared x to the first will just give us 2y squared as the derivative. Remember, y is a constant here. So in the second one, we could think about this as 3y times x to the 8th. And and the derivative of x to the 8th will be 8x to the 7th. Okay, and now we can just simplify that and write this as 2y squared plus 24yx to the 7th. And then the partial with respect to y would be, okay, now we treat 2x as being the coefficient of y squared. The derivative of y squared is 2y. 2 times 2x is 4x, y to the first, plus 3x to the 8th, that's a constant, and the derivative of a constant times y is just the constant. So it'll just be 3x to the 8th. And now to take the derivative, the second derivative, we just focus on this guy here, right? We're just going to take this guy's derivative with respect to x. Now 2y squared is a constant when you're differentiating with respect to x, so its derivative will be 0. And here, once again, we think about 24y as the coefficient of x to the 7th. The derivative of x to the 7th is 7x to the 6th, and then multiply 7 and 24, which will give us 168y x to the 6th. All right, now let's take the derivative of f sub y with respect to y. So we think about 4x as being the constant here, and a constant times y to the first, its derivative is just a constant. And the derivative of 3x to the 8th, well, x is being held constant, so its derivative will be 0. All right, so there's the two pure partial derivatives. Now to get the mixed partial derivatives, I could, for this guy here, I'll just say f sub xy. So I already have fx. Now let's just take the derivative of this guy with respect to y. So the derivative of 2y squared with respect to y will be 4y. And here I have to think about this as 24x to the 7th times y to the first. And 24x to the 7th is constant. Y to the first, its derivative is 1. So we just get 24x to the 7th. And that's our mixed partial derivative there. Now let's do fyx. Okay, so if you do, we've already taken the derivative with respect to y. Let's take the derivative of this guy with respect to x. So remember, don't look at this one. This is already the second partial derivative. We have to think about 4y as being constant, and 4y times the derivative of x to the first will be 4y times 1, or just 4y. And the derivative of 3x to the 8th with respect to x will be 24x to the 7th. Now I want you to notice something here, and if you compare the two mixed partials, notice that these are the same. And so the question is this just a massive coincidence? Did I fudge the problem in some way? Well, no, there's actually a theorem for this. And here we just have some evidence for justifying the theorem. The two mixed partial derivatives are the same. That is, fxy equals fyx, or in terms of the differential operators, you could write it like this as well. This will be true for any continuous function. So at this point, you might say, well, I have a hard time keeping track of the difference between the notations. Well, I'll note that the first variable is the first derivative that you take, and the second variable is the second derivative that you take. And it's not a big deal if you mix them up, because they are exactly the same. So as long as you differentiate with respect to one variable and then the other, it won't make a difference at all. So it's actually 3 derivatives rather than 4 derivatives that emerge out of this, because 2 of them are going to be the same. And if you find one, you know the other. Real quickly, what do these values mean? Well, as in working with univariate functions, fxx and fyy, tell us about the concavity in these two respective directions, x and y. So if xx is greater than 0, it means we are concave up in the x direction. And if fyy is bigger than 0, we are concave up in the y direction. And if they're negative, either is negative, then we have a downward concavity. Now, it's just a little bit harder to do this with multivariable functions because it's a bit more complicated. We have to kind of think about how the two concavities tie in together, and that's why we're also going to need to take in the mixed partial derivatives into account, as we'll soon see. When we calculate a critical point, it doesn't just suffice to look at the second partial derivatives and say, oh, well, if it's concave up, then that critical point must be a minimum, right? Because if it opens up this way, then you'd say, well, you know that you're dealing with a minimum as the critical point. If it opens up this way, then you're dealing with a maximum. Not quite as straightforward when you're dealing with multivariable functions. So we'll just see how the mixed partials come into play.